JMO 2024 problem 1. It says let ABCD be a cyclic quadrilateral such that AB is 7 and CD is 8. Then it says points P and Q are selected on AB. How such that AP is equal to BQ is equal to 3. So AP 3, BQ 3, around 3, and this one is 1. Okay. And it says points R and S are selected on CD such that CR. Why it is 1? Because it says AB is 7. 3, 3 plus 1 is 7. Then it says CR, DS is 2. So CR here 2, DS 2, and SR is what? Because CD is 8. 8 minus 2 is equal to 4. And then it says what? Prove that PQRS is a cyclic quadrilateral. We have 4 rules for proving that a quadrilateral is cyclic. Okay, these are our 4 rules. We can say this for some. First idea here we want to use, or let's write it idea 1. I can say 90% of the problems that you want to prove a quadrilateral is cyclic, you should use one of them. Sometimes you should use 2 of them for proving more cyclic quadrilaterals. Now, here, the first and second rule are related to angles. Opposite angles, sum of opposite angles equal to 180. A1 is equal to B1. For also AMO and JMO 2023, I released full solutions, and in that exam also I use these 4 rules. Third one is related to length. AP, PC is equal to PB, PD, power of point P. If we have this equation, then it is equivalent that ABCD is cyclic. If P is outside, if we extend opposite sides, PB, PC is equal to PAPD. If and only if ABCD is cyclic. Now we want to see which of them is more useful. Okay, we have these 4 rules. If we want to work on angles, because all things here we have are related to lengths 3, 1, 3, 2, 4, 2. So it's better to use which rules? 3 and 4. Now, for 3 and 4, we don't like to draw many lines. If you use 3, we should draw this one, this intersection, and it is not related to ABCD. For 4, we should extend, for example, these two opposite sides. Again, it's not good, but we can extend these two opposite sides. Then it's good, because these two sides are opposite sides of PQRS and also ABCD, and because we know ABCD is cyclic, we can use that. So we should use 4th rule and extend these two lengths. Okay, let's extend AB and CD. Let me extend it like this. Okay, and because we have P, let's call this point T. We know ABCD is cyclic, okay? So we can say what? We can say TA times TB, okay? So we can write TA like this is equal to TD times TC. I write TA times TA plus what for TA times TB, because AB is 7. I can write TA times TA plus 7 is equal to TD times TC. TC is what? TD plus 8. So we can write TD times TD plus 8. Now I want to prove PQRS is cyclic. So I want to prove TP times TQ. Y is equal to TS times TR. If we prove this by 4th rule, we can prove it is cyclic. And we know it is equivalent to TP. I want to make these two equations more similar. So I try to write TP and TQ in terms of TA. TP is what in terms of TA? Let's see. TP, TA is TA plus 3. So TA plus 3 times TQ is what? Is TA plus 4. TA plus 4. Now, I want to write TS and TR. I want to make this side similar to this side. So let me move it here. So TS is what? Is TD plus 2, because here we have TD. I want to write TS and TR in terms of TD. So TS is TD plus 2. And TR is what in terms of TD? TR is TS plus 4. Sorry, TR is TD. Let's write in terms of TD. TD plus 6. Now, from here, we know that TA squared, if we expand left-hand side, it will be TA 7TA. Right-hand side would be TD squared plus 8TD. Now, if we expand left-hand side, it would be TA squared plus 3TA plus 4TA, which is 7TA. 3 times 4, 12. Y is equal to TD squared plus 2TD, 6TD, 8TD plus 12. Now, here, TA squared 78, TA squared 78. Pink part, green part. TD squared, 8TD, so they are equal, and we can cancel these two parts. From here, they are equal, because ABCD is cyclic. So we should prove why 12 is equal to 12, and it's correct, so this one is correct, so this one is correct. And now, by fourth rule, we can say PQRS is cyclic. Okay. So we prove this problem completely only by using one of these 4 rules. So pay attention to these 4 rules. And when you want to prove something is cyclic, try to check all of them, okay? And see the problem is related to angles or lengths. Let me tell you one homework. If you want to solve more homeworks or want to learn more ideas, length of AI, AIA, OI, all these links that are important. It was important also AMO 20, USAJMO 2023. And here we use again these rules. So homework 1. This problem from BMO, British Mathematical Olympiad. I can say the most prestigious national exams, Olympiads, are for USA, which is USAJMO, JMO, AIME, AMC, and BMO, which is for UK, British Mathematical Olympiad Round 2. And the difficulty of this exam is similar to JMO and AMO. So you can try this problem of BMO Round 2 2023. Again, here you should prove some quadrilateral cycling, and again you should use same idea. If you want to learn these background ideas that are repeated in all exams, for all topics, as I said before, feel free to send message to my WhatsApp number in the description. JMO 2024 problem 2. Let m and n be positive integers. Let S be the set of integer points xy with x between 1 and 2m and y between 1 and 2m. A configuration of mn rectangles is called happy if each point in S is a vertex of exactly one rectangle and all rectangles have sides parallel to the coordinate axis. Prove that the number of happy configurations is odd. Okay, again for this one we want to use the idea that we also use in AMO USAJMO 2024 problem 1. And the most useful idea we want to use a small example. So idea 1, small example. And a small example on what? Because here we have two variables, m and n. We can use a small example on both of them, then on one of them. Okay, for understanding problem better, let's see it means what. Suppose m is 1, n is 1, okay, because it says m and n are positive integers. So if you consider m equals n equals 1, then how many points are there? If you want to consider the points, you have 2 by 2 because x from 1 to 2, y from 1 to 2, and then configuration of one rectangle. is called happy if each point in S is a vertex of exactly one rectangle. So we can't have, for example, like this. Why? Because we should have only one rectangle and it should cover all these 4 points. So we have only these and the answer is 1. So let's define for problem AMN. Okay, so A11 we found that is 1. Now let's consider for one of them. Let's consider a small example on one of them, M1 and for any n. So x is from 1 to for creating horizontal figure, let's consider general M and N1. Then we can say x can be from 1 to 2 and y from 1 to 2. So we have these points 1, 2 because n is 1 and x can be 1, 2, 3 to 2m minus 1 and 2m. And let me tell you, in general, we have how many points? 4mn. And each rectangle should cover 4 of them, so we have mn rectangles. That's the reason it says mn rectangles. So each rectangle has exactly 4 vertices between them. Now, 1, 2, 2 by 2m. Let's see the answer is what? We want to see AMN, AM1 is equal to what? Here we can see that we should consider this edge with one of them, for example, with this one or with this one, with one of them. So we should select one column for this. Let me tell you 2 approaches for this part. Approach 1 is that you say, okay. You should say that you have 2m columns, 2m choose 2, then 2m minus 2 choose 2, to 2 choose 2. We should split it into m pairs. But the order is not important. It's not important that you say, okay, it is our first, for example, rectangle, then it is our second rectangle, or vice versa. So we should divide this by m factorial. Approach 2 is what? You can say, okay, for this one, we want to select another column. So how many columns are left? 2m minus 1. So 2m minus 1. Then you say, okay, for example, this one. Then for this one, how many options, how many cases are there that are left? 2m minus 3. Like this, you write 2m minus 1, 2m minus 3, to 3 times 1. And we can prove they are equal. How? Let me tell you. We can say it is what? 2m factorial over 2 factorial times 2m minus 2 factorial. And then for next one, we can write 2m minus 2 factorial over 2 factorial times 2m minus 4 factorial. 2 factorial over 2 factorial times 0 factorial. And we can cancel like this over m factorial. So it will be 2m, I'm sorry, here I should write like this. 2m factorial over m factorial 2 to the power of what? 2 to the power of m. So we can write it as 1 times 2 times 3 times 4 times 2m minus 1 times 2m. All over what? Now we have m factorial times 2 to the m. So we can consider 2 times 1, 2. 2 times, because it is what? It is 1 times 2 times m. So because we have 2 to the m, we consider 1, 2 for this, 1, 2 for this, 1, 2 for this. It's 2 times 4 times 6 to 2m. So we can cancel only even numbers. And this one. So what is left? 1 times 3 times 2m minus 1. Exactly this. Okay, so. And as you can see, it is odd. So our answer is this one, or you can write it also like this. 2m factorial over m factorial 2 to the m, which is odd. Okay. So for n1 and any m, we proved that the answer is odd. Now let's generalize it. Let's consider n is 2. we want to see, and let me tell you something, you don't need it is not needed to calculate AMN exactly is equal to what. We want to prove only it is odd, okay? So let's consider N2. So we have 4 points in each column, and then we can say, okay, first one, second one, third one, fourth one, and so on. Okay, this one and this one. Okay. So 1, 2, 3, 4, 4 rows, and how many columns? 1, 2, 3, 4, all the way to 2m, and here 2m minus 1. Okay, so for this part, we want to calculate AM2. And we can say we want to calculate mod 2 because we want to see only it is odd or even. So let's consider first column. Okay, when you want to solve, let me tell you, it's so much useful also in IMOs. When we want to solve something similar to recursive sequence, we want to use smaller cases. You should see that, for example, the variable represents what? For example, here m represents number of columns. Then consider first one or last one of that. This question is so much useful. It's useful for basic problems in recursive sequence and also for highest level like IMO. Now, let's consider first column. We know that we should select two of them. How many cases do we have? For example, we can consider this one, or we can consider this, or this one, or this one, and this one. We have three options, okay? Three choices. We can solve it with two different approaches. How? Uh, I say, okay, for example, suppose first column is related to this one is related to this one, then this one, for example, is related to this one is related to this one. It means what? Column 1 and column 2 are related to each other. So we can consider like this. Column 1 and column 2 are related to each other because of this part are connected. Column 2 and column 4 are related to each other, are connected. Column 4 and column 3 are connected to each other, and column 3 and column 1. Okay, and then the rest will be what here? Will be a m minus 2 because we removed 4 columns and 2. So here I can say, okay, V1, what are the cases? V1, column 1 can be connected to only one more column, can be connected to 2 columns, can be connected to 3 columns like this. Or because the degree of each column is 2, we have 2 pairs, and because the degree is 2, we can say, okay, if we start from V1, we go some vertices, and at the end we cannot connect to this one. We should go back to V1, okay? So it is union of some disjoint cycles. So consider that V1 is in which cycle? It is an idea in graph that when all degrees equal to 2, then our graph is union of disjoint cycles. So last one is what? V1 is in a cycle that it is what one. Let me tell you like this. How many length of this is what is 2? Length of this is what 3. This is 4 and it is 2m. For this one it would be what? First you should select this one is what? This column. You say okay, 2m minus 1, choose 1. And then we should say okay. For example, V1 we can pair in how many ways? 4, choose 2 over 3. 3 ways. Because it can be like this one, or this one, or this one. Okay, 3 pairs. And then the rest will be what? AM minus 1 and 2. Next one is 2m minus 1 choose 2 times 2 factorial. You see, this is what. And then you say, okay, 4 choose 2 over 3. Then we can say, here we can say, for example, when we multiply by 2, for example, here, v2, v3, or v3, v2. We can ignore these two because we can say, okay, v2, v3, or v3, v2 are similar. Same, but when you select, okay, 4 choose to 3, let me tell you. For example, you want to select column 1, column 2, and column 3. Okay, and you've selected 4 choose 2 over 3, for example, this. Now, for this one, for example, it is v2, it is v3. Then we say, okay, for v2, we want to connect this one to v2, and then this one to v3. So let's see. Now one thing. Is it possible to create this? Because this one is connected to this one is connected to this one, but they are not same. So we need at least one more column. Okay? So as you can see, we can conclude the length should be even. Because for example, this one is red, this one is blue. This one is red, blue, so 3 not possible. The length should be even. So let's consider 4. So the length should be 2 or 4 to 2m. So for this one, for example, this one is red, this one like this, and such. Red means if you consider, for example, this one, we consider this one as red cases, this one as blue blue cases. Okay, so we can say 2m minus 1 choose 3. I will explain here. Then because red, blue, for example, we select v2, v3, v4 without loss of generality. We multiply by 3 factorial, then we say, okay, 4 choose 2 over 3. And for example, 4 choose 2 over 3, we say, okay, v1, v2, v3, v4. We consider, for example, one of them, this one as red, okay, this one as blue. Then we say, okay, v1 is related to v2 with red, v1 is related to v4 with blue. Okay, let's draw this. v2, v3 with blue. So we write like this. And v3, v4 by red. So it will be this unique. Okay. So 3 factorial, 4 choose 2 over 3. We can divide this by 2 if you want to consider clockwise and counterclockwise, but then here we should multiply by 2 because the red one or blue one, we should consider to which of them, red or blue. This one is correct. And we should multiply it by AM minus what? We rejected 4 columns, so AM minus 2. We should remove even number of columns, okay? Because by definition, the thing that is left should have even number of columns. The problem says 2m, 2n. So here, AM minus 2 and 2. And last one is what is 2m minus 1. Choose 2m minus 1 times 2m minus 1 factorial times 4 choose 2 over 3. You can say a0 and 2. You can define a0, 2 is 1. And let me tell you in general, if the length is 2i, it will be what? v1 and the length is, for example, 2i. And we should consider alternatively red, blue. Again, we can say 2m minus 1. Choose 2i minus 1. 2i minus 1 factorial. 4 choose 2 over 3. And am minus what? Am minus I, because we have 2m columns. 2i columns are removed. So 2m minus 2i columns are left. So m minus I and 2. Okay. Now we want to see, okay, some of them, we should prove some of them would be odd. I will tell you also another approach, because if you want to generalize this approach for 6 rows, it will be so much hard. I will tell you another approach after this. So here, it is odd, it is odd, it is odd. Okay, I mean, this part is odd, 3, it is odd, this one is odd by induction, so it is 1. We use induction on m plus n. What about this one? This one odd, it is even, 3 factorial even. Sorry, why I said over 3, over 2, I mean. Over 2, over 2, over 2. So this one is 0, this one is 0, because 3 factorial, 5 factorial, all of them are even, 0. So if you add all of them, 1 plus all these zeros would be 1 mod 2. So we proved it is odd. It was approach 1 here. Let me tell you second approach for solving this part. For approach 2, I want to use one-to-one correspondence. Means what? For example, I want to consider pairs. It means what? Let me say. For example, what are the cases that we have? For first column, we have this case, or we have 3 cases. Let me show you. 1, 2, 3, 4. We have this case, or last one is this one and this one. Okay. Now, what is our one-to-one correspondence? So, for example, suppose we have this, and this one is related to this one. Okay. I say what? I should see that. For example, 1, 3 is related to 1, 4. Okay. Here it is connected to what? It is connected to column 3. This one, this one, this one. And what about this part? 2, 3 is related to 2, 4. So it is connected to this one. So as you can see, if we swap 2 rows, again, we have some rectangles. Here, for example, you should swap 3 and 4, okay? Row 3 and 4. So you have a one-to-one correspondence between these two things, okay? And from here, we can conclude what? If here we have some number of cases, here we have exactly that number of cases, so it will be even. And we should focus only on this part. For this part, we can say what? We can say if, for example, we have something like this and something like this, you can correspond this to, let me show you this one. Or we can, okay, so we know this is equal to this one, so we should focus on this. Now, I want to use one-to-one correspondence. For example, suppose we connect this one to this. If we connect them to different columns, we can again use another one-to-one correspondence. I can say we can connect this one to this, and this part to this part. Okay, so again they are equal, okay, by symmetry. You should switch 3 and 4 with 1 and 2, okay, these rows. It means that if you see from here to this figure and from here to this figure, they are same, okay? So you can create a one-to-one correspondence. Then what case is left if both of them are connected to one column? Okay, so both of them, that column has how many cases? 2m minus 1 cases. So without loss of generality, suppose that they are connected to second column. So we can consider this one. And the rest will be what? A times 2m minus 2. So m minus 1 and 2. And it is what? It is odd. By induction, it is odd. It is also odd. So this one is what? Odd mod 2. Okay? Now we want to generalize this for m and n. Okay? So now let's consider we have m and n. And again, We have 1. Let me draw some of them. 3, 4. 1, 2, 3, 4. Okay, so let's consider we said 1, 2, 3 to 2n, and this one 1, 2, 3 to 2m. Okay, we want to use same thing. Again, how many ways can we split these two n vertices to n pairs? I proved it is equal to 2n minus 1 times 2n minus 3, 3 times 1. So it is odd. So we can consider this case and for other cases, because there are even you can consider in two pairs. Okay, like this one. We had three cases, except this one we had even number of cases. You can consider, for example, this one to this one. You can split them into pairs like this one and this one-to-one correspondence. Okay, they can reach by swapping some rows. Now we can say what? We can say, okay, this case is left. Again, you can say if first one and second one are not connected to same column, for example, without loss of generality, this one and this one. Then you can say, okay, we can consider this one and this one. These two things, again, another one-to-one correspondence, exactly like the thing we did here, okay? And you can write these things and prove them, all of them. So, what case is left? This case. Now, let me consider another 2 rows. Let me put it here. Okay. And now, let me copy. Okay. So, if this one is not connected to here, for example, suppose this one is connected to this one, okay? Then you can swap this one and this one. It means what? You can consider the cases of this one and this one. You can swap these 2 rows with these 2 rows, okay? Then, again, we have another one-to-one correspondence. So we can ignore them because some of them would be even. So we should consider with this. And like this, you can continue like this one and this one. And we should multiply by 2m minus 1 because these two things, these two pairs are connected to which column. Then if, for example, this one is connected to another one, we use one-to-one correspondence, so it is left. So we consider all these things. So we can say AMN mod 2 is congruent to some zeros, some even numbers, plus 2m minus 1 times what? Times am minus 1 and n. So if you use induction on n or on m, or we can say m plus n, we can say this one is odd, so odd times odd is odd. So we proved this problem completely. How we found this idea? By considering small examples. For n2, we found 2 approaches, but one of them was useful. Okay, so how can we understand which of them useful? You should check. When something comes to your mind and you think, okay, maybe it's useful, try to check that, try to generalize that. If not possible, try to check another approach. And we don't know in the beginning which ideas are useful, which ideas not. You should check them, okay? After solving some problems, if you, for example, you don't need to go to the end of that approach. You can, for example, after 2 steps, you can understand it works or not. So we use a small example here. We use this approach. We use this approach. We used recursive sequence, and the idea I told you, you should see m represents what and consider first of that here, first column, because m represents number of columns, one-to-one correspondence, idea 5. And also we used induction idea, this is structure that you use a small example and find some idea and try to prove it by induction. And also induction on sum of something. Let me tell you one homework. You can try this problem of AIMO as homework 1. And this problem of AIMO 2011 problem 4. I told you something here related to recursive sequence and how we solve this one. you should use exactly same approach for solving this problem, and it has two solutions. If you wanted to solve this with one approach, but if you consider from weights, you can reach one solution. If you consider from steps, you can reach another solution. If you want to see how we should start, how we should approach these types of problems, and if you want to learn other important ideas, background ideas that are repeated in IMO, USAJMO, JMO, all these exams, feel free to send message to my WhatsApp number in the description. JMO 2024 problem 3. Let A of n be the sequence defined by A of 1 equals 2 and A of n plus 1 is equal to A of n to the power of n plus 1 minus 1 for each integer n at least 1. Suppose that p is greater than 2 is prime and k is a positive integer. Prove that some term of the sequence A of n is divisible by p to the k. Okay. For this problem, I told you the most useful idea is what? Idea 1 concerning a small example. Again, we want to use this idea like problem 2 and also problems of USAJMO 2024 and also for 2023 and all the exams. This idea is so much powerful. But a small example on what? Let's use a small example on P. Okay? First P that we should check is what? P2? No, because it says P is greater than 2. So the first P is 3. And I want to see, it says K is a positive integer. So you should prove what? You should prove for each power of 3 there exists an element in our sequence that is multiple of that. Okay? So let's see what happens here. A1 is what? Is 2. A2 is what? You should raise A1 to the power of 2. Look, A2 is A1 squared minus 1, which is 3. A3 is what? Is 3 to the power of 3 minus 1, 27 minus 1, 26. A4 is what? 26 to the power of 4 minus 1. And we should continue and write these numbers. Now, I want to prove that let me tell you first, for example, when we have V2 of something, V2 of 24, you should prime factorize 24 and write 2 cubed times 3 and see power of 2 is what? Is 3. For example, V2 of 18 is what? If you prime factorize, it's 2 to the 1 times 3 squared. Power of 2, 1. So V2 of 16 is what? 16 is 2 to the 4 is 4. Okay, V2 of 5 is what? Is 0, because power of 2 is 0. V3 of 18 is what? Is 2, because 3 is squared, and so on. Now we want to prove that V3 of, for example, AI is large, A something. If we consider V3 of AN plus 1, if we use this equation, it will be what? V3 of AN to the n plus 1 minus 1. When we see this, it is similar to a theorem. It is what? Lifting the exponent. Okay, or LTE. It says what? Because here we know our P is odd. If P is an odd prime, and P doesn't divide X, so it's idea 2. P doesn't divide Y. It was also useful in AIME. I will tell you at the end of this solution. The AIME problem was what? And you can do that one as homework. And I think I released full solution of that problem. So if you saw my previous videos, you could solve this problem if you combine this with a small example. So if we divide this, then we can say Vp of x to the n minus y to the n is equal to, for plus also we have formula. When p is 2, we have formula. We have 3, 4 cases. Vp of n, okay? Now we want to use this. So here, if we want to use this, we know that 3. Let's see the conditions that should be satisfied to use this. 3 shouldn't divide an. 3 shouldn't divide 1. Here, 3 should divide an minus 1. And then we can apply this. So first, let's see what happens. These 3 conditions, we know this one is always correct. If an because of this should be 1 mod 3. Okay, if an is 1 mod 3, 3 doesn't divide an. So we should find ans that are 1 mod 3, if it is possible. Let's check, can we use this or not? So let's move it here. We should consider these numbers mod 3. First one, okay. So a2, you should raise to the power of 2. Previous one. This one raised to the power of 3. Raised to the power of 4. Okay, so if you check a1 is 2, or instead of 2, you can write negative 1. Negative 1 squared minus 1 is 1 minus 1, 0. 0 squared minus 1 is minus 1. As you can see, 26 is minus 1. Again, minus 1 to the 4 minus 1 is 0. Minus 1, 0. So we cannot reach an that is equal to 1 mod 3. Okay, so here we don't have an that is 1, but like AIME problem, if it is even, you can consider an squared. Then an squared is negative 1. So as you can see, it is a1, it is a2, a3, a4, a5, and easily by induction we can prove a sub odd numbers are negative 1. So if we consider n odd, suppose n is odd, okay? So v3 of an plus 1, let's see is what? Is v3 of an to the n plus 1. Because n is odd, you can say n is, for example, 2k minus 1. Okay, so let's write v3 of 2k is equal to a 2k minus 1 to the power of 2k minus 1. And we know a 2k minus 1 is negative 1. So if we consider v3 of a 2k minus 1 squared to the k minus 1, then this part is 1. You can call this one, for example, as x and this one as y. So because x squared is 1 mod 3, so x minus 1 is multiple of 3, and this one is non-multiple of 3, this one is non-multiple of 3. And we can use what? We can use LT. So if we use LT, it would be what? Let's write. We can write it's equal to v3 of a2k minus 1 squared minus 1 plus v3 of what? K. Now, because we had k in the problem, let's use another variable. For example, r. Okay, so r, 2r minus 1 to the 2r, 2r minus 1 squared to the r, 2r minus 1 squared plus v3 of r. Okay. If r is multiple of, suppose, for example, r is equal to, it says for any power of 3, for example, any power of p, like k, prove that there exists an element. So if we define r as 3 to the k, so it will be what? It is at least k. V3 of this is at least k. And also we can say k plus 1 because it is also multiple of 3. So this one is multiple of 3 to the k because v3 of that is multiple of k plus 1. So we proved that v3 of a 2 times 3 to the k is at least k plus 1. So 3 to the k divides this. Also you can say v3 of a 2 times 3 to the k minus 1 is at least k. So for 3 we could prove this problem. Now let's check another number. Here we can see that We can try to generalize it, but let's check also P5 to see what can we say for P5. Again, if we consider our numbers, first number is 2. Okay, so for P5, if we consider first one is 2, next one is 2 squared minus 1, 3. Next one is 3 cubed minus 1, which is 26, like this. And if we consider these numbers mod 5, so we can write 2, 3, 26 is 1, it is A1, A2, A3. Next one is what? 1 to the power of 4 minus 1, 0. Next one is what? It's A4, A5. So 0 to the power of 5 minus 1, negative 1. A6 is what? Negative 1 to the 6 minus 1, 0. A7 is what? 0 to the power of 7 minus 1 minus 1. A8 is what? Negative 1 to the power of 8, 0. So obviously, because when we have negative 1, it is A odd, then next one is A even. Negative 1 to the power of even is 1 minus 1, 0. And again, we can say 0, negative 1. So from here, we have 1, 0, 1, negative 1. From here, A4, we have 0, negative 1, 0, negative 1, 0, negative 1, and so on. Now, I know that A, again, 2k are even numbers. A, 2k are 0. So we can say, if we want to calculate, again, we want to apply LTE, V5 of A2k is equal to what? V5 of A2k minus 1. And suppose A2k, k is at least 2. Or AK is at least 3. Okay, at least 6. The previous one is negative 1. A2k squared. No. To the 2k minus 1. And because we know A2k minus 1 is negative 1 from this one, so we can say V5 of A2k minus 1 squared. k minus 1. Now we know it is 1. Mod 5. So these conditions would be satisfied if you consider this one as x, this one as y. 5 divides this minus 1 because it is 1, because this one is negative 1, squared is 1. Now we can apply LTE. It will be V5 of A2k minus 1 squared minus 1 plus V5 of k. Again, because we have k, I should use another variable. Pay attention to this point, because maybe the person that want to check your answer think that this k is the k problem says, let's write s. It's better to not use same variables. So 2s minus 1, this s, 2s minus 1, 2, v5 of s. So if s is 5 to the k again, we can say what? It's at least v5 of that, at least k plus 1, or you can say 5k minus 1. Then it's at least k. Okay? And this number is multiple of 5 to the k. Let's check one more prime, 7, and then we will generalize it, okay? If we check for 7, p equals 7. Okay, let's check p7. Again, first number a1 is 2, a2 is 2 squared minus 1, 3. a3 is 3 cubed minus 1, 26. 26 mod 7, we can say is negative 2. a4, negative 2 to the 4, 16 minus 1, 15, which is 1. a5 is what? 1 squared minus 1, 0. a6 is what? 0 squared minus 1, negative 1. a7 is what? Negative 1 to the 7 minus 1, negative 2. a8 is what? Negative 2 to the power of 8 minus 1. And if you want to calculate negative 2 here, we should use little Fermat's theorem. That's the reason that we are checking more small example. We can find more ideas that are useful. Idea 3. Let me write it here. Little Fermat's theorem. It is what? you can say a to the p is congruent to a mod p. P is prime. Or one explanation is this, or you can say GCD of a and p is 1. If GCD of a and p is 1, then a to the p minus 1 is 1 mod p. And you can prove both these explanations are equivalent. And if you want to prove this, you can. I can explain for you the proof, but you don't need to prove it for the exam. But if you wanted to know the proof, you can send message to my WhatsApp number in the description. You should consider A2, A3, A to P minus 1A, and prove that it will be mod. It should be 1 to P minus 1 mod P in some order. And then you should consider the product and cancel P minus 1 factorial from both sides. But if you want to know the rigorous proof, as I said, you can send message to my WhatsApp number. Negative 2 to the power of 8. I want to see this one mod, then minus 1. This one mod 7 is what? So it's 2 to the 8 because 8 is even. And we know 2 to the 7 is 2 because of this part. Or you can say 2 to the 6 is 1. It is 2 squared, okay? It's 4. 4 minus 1 is 3. A9 is what? So if you check negative 2, 1, A9. Okay, next one is what? 3. 3 to the 9 minus 1. 3 to the 9 is what? We know that 3 to the 6 is 1 mod 7 by little Fermat's theorem, so it will be 3 cubed. And 3 cubed is 27. 27 is negative 1 mod 7, so it's negative 2. So let's see, do we have this period? 3, negative 2, and so on. So let's see. Here it is, we should raise previous one to the power of 2. We should raise previous one to the power of 3, to the power of 4, to the power of 5, the power of 6. And we can say it is to the power of 7. We can say to the power of 1. A to the 7 is A. This one again is to the power of 2, to the power of 3. And as you can see, this negative 2 is to the power of 3. So next one will be same. So if we consider this period, but as you can see, it starts from 2. Here it starts from negative 2. So let's write and see. Next one, beginning number would be what? Let me check this. Okay, a to the 10 is what? We should raise to the power of 4, it's 1. A to the 11, it will be 0 to the power of 5. A to the 12, it's to the power of 6. And it's negative 1. And again, we have same thing. Then a to the 13 will be to the power of 1. It's negative 2. So as you can see here, these numbers are 1. A10, A4, the period is 6. You can say A, 6K plus 4 are 1 mod 7, okay? Again, I don't want to write K, for example, W. So if I consider X6W plus 5, I want to find V7 of this, okay? So V5 or V7 of this is what? V7 of X A6W plus 4, the 6W plus 5 minus 1. And because it is 1, we can apply LT. It will be V5 of V6W plus 4 minus 1 plus V5 of 6W plus 5. So I want to do what? 6W plus 5. And this one we know is at least 1 because it is 0. And we want that this one be multiple of 7. Sorry, why I wrote 5? I should write 7. V7, it is at least 1. Because you can prove by induction because we have these two things. Again, this part will be repeated. Okay. And it is at least 1. So this one should be at least what? At least k minus 1. Then some of them will be at least k. And then this one will be multiple of 7 to the k. 6w plus 1. if it is 0 mod 7 to the k minus 1. I should find at least one w that it's multiple of 7 to the k minus 1. It's easy because you say, okay, 6, it's negative 5 mod 7 to the k minus 1, and 6 has a, we can say, multiplicative inverse mod 7 to the k, because GCD of 6 and 7 to the k minus 1 is 1. Then there exists a number, we can call it 6 inverse. It is a number, an integer, not 1 over 6, but in modular arithmetic we can write like this. Or if it is not good for you, you can say, okay, multiplicative inverse of this, suppose it's b. 6b is 1, mod 7 to the k minus 1. So we can multiply both sides by b, so w is congruent to negative 5b mod 7 to the k minus 1. So you can add 7 to the k minus 1 to reach a positive integer. So we have infinitely many w that satisfy this. And for this multiplicative inverse, I can prove it for you. Let me tell you idea 2, idea 3, idea 4. Suppose GCD of a and b is 1. Then there exists x such that ax is 1 mod b. Okay, so x is multiplicative inverse of a mod b. Okay. The reason is what you should consider a to b minus 1a. And we want to prove that one of them is 1 mod b. And then the problem will be proved. So first I want to prove that they are different. They are different mod b. 1, 2 to b minus 1. Okay, mod b. How we can prove this? First I want to prove that they are different mod b. If IA is congruent to JA mod b, we have a rule in modular arithmetic. If AM, or we can say AB, is congruent to AC mod M, then it is equivalent. You can divide both sides by A, but you should pay attention that you should write M over GCD of M and A. It is so much important. And we can prove it. If you want to know the proof, again, you can send message my WhatsApp number. This one, then by this approach, you can say, okay, we can divide both sides by A, but GCD of B and A is 1, so mod B. But we know these coefficients are 1 to B minus 1, so they cannot be congruent mod B. So they are different, and none of them is 0 mod B, because if it is 0 mod B, we know A and B are relatively prime, and 1 to B minus 1 are non-multiple of B. So we can conclude what? They are different mod b and not 0, so they should be 1 to b minus 1 in some order, because number of them equals b minus 1. So one of them is equal to 1, that's multiplicative inverse. For example, k times a, t times a is 1, and exactly that is multiplicative inverse that we want. Proof of Little-Fermat's theorem is similar. Now that we prove this, so we have multiplicative inverse, we can multiply, and then we have a good W. So we proved for 7, and we understood, okay, we should find this period, and we should pay attention to Little-Fermat's theorem. Now let's generalize it. You know, A1 is 2, A2 is 3, A we should raise to the power of 1 here, we can consider power of 2, power of 3. And this one is what? 26, and so on. Now we know until AP minus 1, we should raise to the P minus 1. Then for AP, we can consider raised to the 1. So we have this length. Then again for until A2P minus 2, we should write to the power of P minus 1, like 7 that we said, until 12. Okay. Length of this period is P minus 1. Okay, so if we find equal, for example, A1 equals AP, then these two things will be similar. Again, for next one, just consider A2P minus 1. should raise to the power of 1 to a 3p minus 3. It is p minus 1 and so on. Like a small examples that we checked, we want to find something 1 or negative 1. Let's see how we can find that. If we use little Fermat's theorem, we can say, for example, for AP, or let me tell you, AP minus 1. AP minus 1 is what? Is equal to AP minus 2 to the power of P minus 1 minus 1. So we have two cases. Case 1. If AP minus 2 is 0 mod P, then what happens? AP minus 1 is what mod P? Calculate this. 0 minus 1, negative 1 mod P. Case 2. If AP minus 2 is not 0 mod P, means non-multiple of P, so relatively prime to P. So AP minus 1 would be what? This one would be 1, 1 minus 1, 0. Okay. And as you can see, for these cases also we have same thing. Okay, because when you raise to the power of P minus 1, we said it's equivalent to P minus 1. So the previous one is important. If it is 0, then next one is negative 1. So let's consider cases. Let me move it down. And okay. If previous one is 0, this one would be what? Negative 1. Negative 1 to the 1 minus 1 is minus 2. And minus 2 squared minus 1, 3. Or if it is not 0, then this one would be 1. And I'm sorry. If it is not 0, this one would be 0. Then 0 to the 1 minus 1 is negative 1. Negative 1 squared. 1 minus 1, 0. Now we can see the first one from second group or second box. Can be start with negative 2 or negative 1. Okay. Now, if again next one, for example, is negative 2, the next one obviously will be negative 2 like this. So, again, we can write for this part 0, negative 1, negative 2, 3, or 0, negative 1, and 0. So we can go to this part, or this part, or this part, or this. We have these 4 cases, okay? So let's check them. Okay. If we check them, we can see that this part is what? We can go from negative 2 to negative 2, or from negative 1, for example. Suppose we are focusing on only these parts. Why here I said? Oh, sorry. Here I should correct this. This part, negative 2, 3, negative 1, and 0. Okay, this, or this one, or this one, or this. If we go from this part to this part, we can show it like this, negative 2 to negative 2. If from this part we go to this part, negative 1 to negative 1. If we go from this part, negative 1, to, for example, this part, that is 2. After that is important. If from negative 1 we go to negative 2, and from negative 2 again to negative 2, it will be similar to this. Or if we go from, for example, negative 2 to negative 1, and then here, it will be here. Because after that, next step, we go to negative 1 and negative 1 and negative 1, and so on. Or maybe we go from negative 1 to negative 2, negative 2 to negative 1. So we have these 3 cases, and we should check them. Okay, so for this one, negative 2 goes to negative 2, negative 1. Let me write this 0 below this one. It's for A2P minus 2. And so, like previous cases, when we found, for example, some 0, we should consider, okay, A5 in terms of A4. For example, we found that x6w plus 4 is 1. And then for next one, we use this one. So previous one is important. So let's calculate for these zeros. Let's calculate before that is what? Okay. we know something to the power of p minus 2. So we know it is ap minus 2, for example. ap minus 2 is what? Is 0. ap minus 2, or if we want to write general form, it is 2p minus 3 raised to p minus 2. So it will be what? A p minus 1 times z plus p minus 2, okay? It is equal to what? It is equal to a times p minus 1 times z plus p minus 3 to the power of p minus 1 z plus p minus 2 minus 1. If we consider this part mod p, we can say this number mod p minus 1 is what? Is 1 if it is not 0. And we know it is not 0. Because if it is 0, then 0 minus 1 is negative 1. And this p minus 2 should be for this purpose. Okay. We are considering which numbers? We want to consider these numbers, okay? So as you can see, for example, when it is 2 times p minus 1 plus z is 1. Z is 1, p minus 1 plus p minus 2, 2p minus 3. If z is 0, it will be this, okay? So p minus 1 times z plus p minus 2 minus 1. So it is not 0, because if it is 0, then 0 minus 1, negative 1. So next one, this one will be negative 1, not 0. So it is not 0, so we can use little Fermat's theorem, and the power of this one is 1. So it is a p minus 1 z plus p minus 3, the power of p minus 2 minus 1. And we know this part is what? This part is 0. Okay? So we can say a to the power of p minus z plus p minus 3 to the power of p minus 2 is 1 mod p. And we can say what? We can multiply by a p minus 1 a this sum. And then this side will be a to this one to the p minus 1 by little Fermat theorem is 1. So a times p minus 1 z plus p minus 3. So we can conclude previous number is 1, okay? So when we have 0, previous number is 1. When we have 0, previous number is 1, okay? Now we can use LTE, lifting the exponent. How? We can say what? We can say, okay, a to the p minus 1. We want to find what? VP of this. Okay, VP of a, this one, p minus 1 z plus p minus 2 is equal to what? Is VP of a p minus 1 z plus p minus 3 to the power of p minus 1 z plus p minus 2, by definition assumption of the problem, minus 1. And because we know it is 1 mod p, so this one minus this one is multiple of p, so assumptions of conditions of LTE will be satisfied. So we can write it as VP of a p minus 1 z plus p minus 3 minus 1. This one is at least 1 because we proved this one is 1 mod p, plus VP of p minus 1 z plus p minus 2. Okay, so if we prove that this one can be multiple of p to the k minus 1, then for this case, problem will be solved. How we can prove this part? We should say, okay, p minus 1 z plus p minus 2 should be 0 mod p to the k minus 1, right? So we can say p minus 1 times z congruent to 2 minus p mod p to the k minus 1. So because p minus 1 GCD of this and this, GCD of these two numbers are 1, we can easily prove. So we can multiply by multiplicative inverse of p minus 1. We prove there exist, okay? By idea 4. Let me tell you why the GCDs are, let me cut it. Let me tell you why the GCD is 1, because if you consider GCD of p minus 1 and p to the k minus 1 d. Then we know d divides p minus 1, d divides p to the k minus 1. Okay, and from here we can say p is 1 mod d, and from here p to the k minus 1 is 0 mod d. So from here you can raise both sides to the power of k minus 1, so p to the k minus 1 is 1 mod d. And by considering these two things, we can say 1 is 0 mod d. Okay, so d divides 1, the difference, and d, because by definition of GCD that is positive, d is 1. There are lots of other ways. You can say, okay, if consider GCD of these two things, because d is a divisor of this, is p to the power of something, and p to the power of something is not divisor of this. There are lots of ways to prove this. Okay, so because we can multiply by multiplicative inverse, so we can say z is equal to p minus 1 inverse. We can write it like this. And as I said, this is integer, not 1 over this. We consider mod p to the k minus 1. Okay, z is this one. And then this one will be satisfied, so this one is at least k, and you can add p to the k minus 1 to reach a positive number if it is negative. There are infinitely many with z. So 1, 2. Now let's check case 2. Okay, if negative 1 goes to negative 1. Okay, for this negative 1 goes to negative 1, we should erase this part. Let me erase this part. Negative 1 goes to negative 1. So let's move it here. Okay. And then we can say what? Negative 1 goes to negative 1. Next one, 0. And we can say we wanted negative 1 or 1. And this is 0. So this is what AP plus 1. This one is 0. A2P is also 0. So these numbers are what? Because the length is P minus 1, we can say A P minus 1 times, for example, T plus what? For example, P minus 1 plus 2. Okay? Plus 1, sorry. If T is 1, it is P. If T is 2, it is 2P minus 2 plus 1. It will be 2P minus 1. They are negative 1. Okay? Mod. And because from negative 1 we reach negative 1, again we reach negative 1, and so on. Now, if we consider a p minus 1, now we want to consider. And this number, next one, reaches to the power of 2. Equivalent to power of 2. So let's consider Vp of a p minus 1 t plus 2. Okay, so these numbers. It is equal to Vp of ap minus 1 t plus 1 to the power of p minus 1 t plus 2 minus 1. Okay, and then we can say what? We can say it is even and it is negative 1. So we should write like a small examples that we check. ap minus 1 t plus 1 squared of this over 2. P minus 1 t plus 2 over 2. P minus 1 is even, 2 is even, so sum of them is even, minus 1. Now, conditions of LT are satisfied because this is negative 1. Mod P, this squared is 1. So this minus 1 is multiple of P. So we can apply LT. It will be A P minus 1 T. Let me write. P minus 1 T plus 1 whole squared. And minus 1 plus Vp of this one is P minus 1 T plus 2 over 2. Okay, so we know this one is at least 1. We should prove why this one can be at least K minus 1. So we should find a good T that, because 2 has no effect on P. So if it is multiple of P to the K minus 1, this one also is multiple of P to the K minus 1. So P minus 1 T plus 2 should be 0 mod P to the K minus 1. Again, like previous one, you can take 2 to right hand side and multiply by this inverse. So T is congruent to negative 2 times P minus 1 inverse mod p to the k minus 1. Okay, so we proved also this case. Okay, for this part, -1 goes to 2 without loss of generality. Suppose, for example, here we have -1. Sorry. For this one, -1, and this part, -1 goes to -2. So this length, and this part, 3p minus 2 to this one. Okay, -1, 0, 0. Then it goes to what? To -2. You know, before -2 is -1, and -2 goes to -1, again 0, 0. Okay, and so on. Again, -1 goes to -2. Like this, -2 goes to -1. So we can say our period is this part. Okay. So let me erase this part. Okay, let me raise the power of what? Here, raise the power of 1, raise the power of 2, raise the power of p minus 1, again, raise the power of 1, raise the power of 2, raise the power of p minus 1, raise the power of 1, raise the power of p minus 1, raise the power of 1, raise the power of p minus 1. Okay, now we can consider what? Let me erase this part. Okay, the length of this period is 2p minus 2. Okay, and it's not important. It starts from -1, -2 here, or -2, -1. Now, what number is good here? We want to find the one that we had. We said it is what? -1, 0. Before -2, -1, 0, 1. -2, -1, 0, 1. 0 and 1. We have this. Okay. So this number is what? A 2p minus 2, 2p minus 3, 2p minus 4. Okay, so 0, 1. It's a 2p minus 4. What's the next number that has this property? Next one is a. You should add 2p minus 2 because look, p plus 2p minus 2 is this one. 2p minus 2. So we can write 2p minus 2. For example, I plus 2p minus 4. Okay. Now we should consider next number that is 0 and apply LTE. We know. So if we consider VP of A times 2p A sub 2p minus 2i plus 2p minus 4 plus 1 2p minus 3, this is congruent to what? VP of A 2p minus 2i plus 2p minus 4 to the power of 2p minus 2 by assumption of the problem plus 2p minus 3 minus 1. Now we can apply LTE because this this is 1 mod p. By induction you can prove, and we proved this in previous part. Then because it is 1, this minus 1 is divisible by p, and this one are not multiple of p. So we can write VP of A 2p minus 2i plus 2p minus 4 plus VP of this, the power 2p minus 2i plus 2p minus 3. This one is at least 1. We should see for which I it is at least k minus 1. Then this part will be at least k. And the problem will be solved completely. So 2p minus 2i plus 2p minus 3 should be 0 mod p. Okay? Mod p to the k minus 1. So we can say 2p minus 2i should be congruent to 3 minus 2p mod p to the k minus 1. If you take this to right hand side. And we should multiply by this inverse because this and p are relatively prime because p is odd and p and 2 are relatively prime. So p and p minus 1 also relatively prime because it is 2 times p minus 1. Okay. So we can multiply by this inverse. So I is congruent to 3 minus 2p times 2p minus 2 inverse mod p to the k minus 1. So if it is negative, you can add p to the k minus 1 as much as you want, and you can find infinitely many good i's. So in all cases, we proved this problem. Let me tell you some homeworks. Okay, try this problem as homework 1, AIME 1 2020. You can solve it with similar idea. If you want to solve more problems from this idea, as I said before, or wanted to learn more background ideas, how to approach difficult problems in IMO, JMO, AMO, feel free to send message to my WhatsApp number in the description. JMO 2024 problem 4, let n greater than equal 3 be an integer. Rowan and Colin play a game on an n by n grid of squares where each square is colored either red or blue. Rowan is allowed to permute the rows of the grid and Colin is allowed to permute the columns. A grid coloring is orderly if, no matter how Rowan permutes the rows of the coloring, Colin can then permute the columns to restore the original grid coloring. Look, because pay attention, Rowan are permute rows, Colin columns, okay? No matter how Colin permutes the columns of the coloring, Rowan can then permute the rows to restore original grid coloring. In terms of n, how many orderly colorings are there? It says n at least 3, but let's also check. I want to use a small example, okay? And by small example, I want to find the idea. And I want to see which tables are good and then prove it. We solved many problems of JMO and AMO by small examples. So let's consider a small example on n1. For n1, first one cannot permute, second one cannot permute. Because we have only one row and one column, so all of them are good because you can restore the original grid because it doesn't change. So the answer is 2. If n is 2, let's check this. If all of them have same color, for example, A, then it's good because again it doesn't change. So 2 cases here. Here it was 2 for n1 because all of them black or all of them white. 3 of them black, for example, let's consider 3 of them black. Without loss of generality, suppose it is this. If R permutes these 2 rows, then we have what? This. And here we had 2 blacks, 1 black. Now here we have 1 black, 2 blacks. If we want to permute columns, we can see that this one still will be 2 if you permute columns. So we cannot reach this one, okay? By permuting columns, number of blacks in this row doesn't change, okay? So we can say what? This one is not good, 0. If we consider 2 blacks can be like this or like this one. 1 black is similar to 3 blacks, so it's okay. And here we consider, for example, 4 blacks or 4 whites. Both of them are same and they were good. So for this one, again, if you permute rows here and if you permute columns, you cannot reach original diagonal. Okay, so this one again, 0. This one, for example, if you permute rows, it will be what? It will be like this. If you permute columns, it will be sorry. If you permute rows, it will be this one. If you permute columns, it would be this one. And obviously, you can first permute columns. You can reach original diagram by permuting rows after that. So we have 2 cases. 2 blacks like this or 2 blacks like this. So how many good cases? 2 plus 2, 4 good cases. Okay, so for n1, the answer is 2. For n2, the answer is 4. Okay? And the problem says start from n3. In n3, we can find some good results. So for N3, let's try an example, okay, to see it's good or not. Because we cannot check all cases in the beginning. For example, this. Suppose we, for example, permute these two rows. Then it would be what? This one, this one, this. By permuting columns, you cannot reach original diagram. Why? Because if you permute columns, again here we have two blacks, here one black, but here we have two blacks and one black, but it doesn't change. So we understand that we should pay attention to number of blacks in each row and number of blacks in each column. So suppose, for example, we consider here we have R1, R2, R3 blacks, C1, C2, C3 blacks. And for example, suppose we permute R1 and R2 as an example. So this one will be R1, R2, R3. When you permute these two rows, number of blacks in each column won't change because in each column these two will be switched and this one won't change. So number of blacks again will be C1, C2, C3. And now if you want to permute columns, number of blacks in rows won't change. Okay, so we can say that R1 should be equal to R2 if you want to reach this one again by permuting columns. Okay, because if you permute this, these things won't change. So R1 should be equal to R2 if you want to reach this. So R1 should be equal to R2. Similarly, R1 should be equal to R2, R3. And similarly, again, we can say C1, C2, C3. So because we know now, sum of R1, R2, R3 will be number of blacks. R1 plus R2 plus R3, number of blacks, is equal to C1 plus C2 plus C3. Okay? It is equal to number of blacks with double counting. Okay, we can call this idea, it's important. Changing viewing angle, we can call it, or professional name, double counting. In AMC also, I saw a problem with this idea. So we can conclude what here? We can say, okay, R1, R2, R3, because they are equal, is 3R1. Here it is 3C1, so R1 is equal to C1, so all of them are equal. R1 is equal to R2 is equal to R3 is equal to C1 is equal to C2 is equal to C3. Exactly, with the same approach, you can generalize it for n, general n, that number of blacks in each row should be equal to each other and also equal to number of blacks in each column and row. And now, we should consider x is what? Okay, x can be what? Number of blacks can be 0, 1, 2, 3. Okay, so x can be 0 or 1 or 2 or 3. And 0 and 3 are similar. So let's check one of them only. 1 and 2 also are similar because black and white problem is symmetric with respect to black and white. So let's check first x0. It's good because if you permute rows, the table doesn't change, and also for columns, so we have one good table. For 3 also we have one good table. Then now let's check x1. If x1 in each row and each column we have one black. Without loss of generality, consider it is this because this, and we know we have 3 factorial of this type, okay? All of them are similar because the blacks should be in different rows and different columns because x is 1. And each row and each column we have exactly one black. Now, suppose, for example, we permute column rows, okay? For example, it is 1, 2, 3. If we permute, for example, you say, okay, 1, 2, 3. So 1 here, it's this one, 2, 3. Then it's not important that our permutation is what? When we want to permute column, I say, okay, in which row we have a, let me tell you, you should pay attention when you want to permute column. You should pay attention in first row, our black is what? So you should move it to this. In second row, our black is what? You should move it to this. In third row, our black is what? You should move it to this. Okay? And then it would be a permutation. Why? Because you say what? You say third column should go to first column. First column should go to what? Second column. Second column should go to what? Third column. For n, as you can see, for each number, we have one out degree, one in degree always. Why? Because we know that in this column, third column, want to go to what? We have only one black in third column, so then it will be it has one out degree, and only one black should go to third column because we want to reach these. We have only one black in third column, so it has only one in degree. And because we have one in degree and one out degree, then it creates a permutation. You can say, okay, 3 goes to 1, 1 goes to 2, 2 goes to 3. And in graph, we can consider a permutation graph. I solved Sumac problem with this idea. Sumac problem. I will tell you at the end the problem was what. And when we have a graph and in degree and out degree of in degree means what? Input here it's 1. Out degree is what? 1. So if you have a permutation graph and in degree and out degree of each vertex is 1, then you can conclude it is union of disjoint directed cycles, and then it is exactly, we have a one-to-one correspondence to a permutation. Okay, so we have these things. And now we can see, okay, so how many good graphs are there? 3 factorial. For x2, how many good graphs are there? Similarly, because when we have 2 blacks, we have 1 white. Okay, the problem is symmetric with respect to white and black, so we can say 3 factorial. So the answer for this part is what? 2 times 3 factorial plus 2 times 1. 2 times 3 factorial plus 2 times 1. Now let's write it. n3, 2 times 3 factorial plus 2 times 1. But is it 2 times 2 factorial plus 1? No. Plus 2? No. Maybe the reason that it says n at least 3 is this. So let's check n4. Okay, and we want to see for n4 what happens by the thing we reached here. So in this case, we want to consider first again x0 to x4. But we know again x0 and 4 are similar. And we should check x0, x1 and x2. Okay, these 3 cases. 3 is similar to 1, 4 is similar to 0. Okay, so x0 is good. So for x0 and 4, you have one case for each of them, so it would be 2 cases. Now, let's consider x is 1. Again, exactly by the same approach we did here for x1, it would be good, but because we have x1 and 3, it will be what? 4 factorial. Because for 1 in each row and each column, we have 1. So in first row, you select 4, for example, this. Then you select, okay, for next one, we cannot select this. So 3 cases are left, 3. Then here you cannot select this because in each column also we have 1 black. So you have 2 cases, this one and last one, this. Okay, 4 factorial for this one, 4 factorial for this one, 2 times 4 factorial. Now let's check x2, okay? And here, by considering x2, we can understand that can we have x except 0, n, and 1, and n minus 1? Now, in each row and each columns, we have exactly 2 blacks. In first row, without loss of generality, suppose first 2 cells are black. Now, because we know that in this column, we have 2 blacks, because x is 2, without loss of generality, suppose next black is here. But for next black in this row, it can be here or here, okay? These 2 are similar, so we can consider one of them. So let's consider these 2 cases. This black, this black, this one is black, or this one is black. This one is black. Then for this one, because we know in these 2 rows, in first 2 rows and first 2 columns and first 2 rows, we have 2 blacks, so other blacks are exactly here. It would be unique. And what about this case? We know that this column, we have two blacks, one of them is this, one of them one of these two. By symmetric, you can consider this one. Then in this row, we have two blacks. This column, we can't have black here, we can't have black here because two, we can't have black here. So if we consider the black here, then for this row, we have problem because we should have two blacks. Or we can say for this row, we should have two blacks, this one and this one. And then for this row, because this column again has two blacks, so the only cell that is left is this, okay? Because if you place it on any other cell, then we have more than two blacks in one row or one column. So you should consider these two cases. And I want to reach contradiction for both of them. How? For this one, I permute these two rows, and let's see what happens. If we permute these two rows, then we have, let me write it with ink. These two are black, these two, and these two. Okay. Now, because if you want to go back to this one, so because of first row, we can only permute columns. We should move these two rows to this part, okay? Because of these two blacks. They are here, we should move them here. Then as you can see, then this part goes to this part, and then here we have in fourth row we have problem. If you want to correct first row, then in fourth row we have problem. So it is not good. Now, for next one, here they are consecutive blacks. In this row, they are not consecutive. So if we move them, then we cannot reach a good table. Why? Because it would be what? This one, 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 this one. So if you want to permute columns, these two can, let me tell you, if we make these two things adjacent, let's see what happens. So here we can reach contradiction. How? Because here it is white. If you want to go back to this part, we should move this to one of these two cells, okay? This column. Then what happens? This black also goes here, okay? And we know here we don't have any black. So that's a contradiction. So we should move these to one of these two columns, then this one also moves one of these two cells. But here it should be white. Both of them should be white. And that's a contradiction. Again, it's not good. So again, x1 and 2 are good. So 2 times 4 factorial, 2. It would be what? 2 times 4 factorial plus 2 times 1. And we can guess for n, our answer is what? Can you guess? 2 times n factorial plus 2 times 1. Let's prove this. Now if we work on general n, okay, now let's consider n by n. Again, obviously for x0 and n, it would be good because the table doesn't change. So two cases. And now I want to consider x1, again without loss of generality, because in each row and each column you can consider one row. With the same approach like this, you have one input, one output, you can consider permutation graph and one-to-one correspondence to a graph. So for x1 and n minus 1, each of them n factorial cases. Now I want to reject x2 and then generalize it for xr. So we want to consider x is from 3 to n minus 2, okay? So let's check, for example, here. Oh, sorry. From 1 to n minus 2. So let's show this from 2 to n minus 2. We want to say all of them are bad. So here, if we consider we have x blacks in each row and each column, and x is between 2 and n minus 2, we can say what? I can permute rows, let me write R, such that, for example, in first column, all x blacks are consecutive like this. Then we should be able to permute columns to reach our original table. Because when you move columns, then you should move this column to other column. It means that in our original table, so suppose our original table was this, we reached this one, and we want to reach our original table here by permuting rows, and we reach this, and we want to permute columns to reach our original table. Because when we permute our column, this column, for example, goes to another column. But we know that we have x consecutive blacks in the beginning. Okay, first x cells are black. So it means that in our original table, we had a column that first x cells are black. Okay, like this, you can do it for any other. Let me erase this. For example, suppose we have x is 4, for example. I consider this one, I permute to reach this one, and this one. And when we permute columns, we should move this column completely. So again, we can conclude we have a column that has this black, these two blacks, this black. So like this, because we can place these x blacks in any of the cells in first column, so we can create how many columns for first column, how many blacks, and choose x. And we know for each of them we should have one column in our original table that is equal to exactly that. So it is less than or equal n because we have n column. Okay, so and we can like this one, we can create we can change first column to any of the cases and choose x. And so in our original table we should have all of them. So n choose x is less than or equal n. If you had question about any part of the solution or wanted to learn other ideas, feel free, as I said before, to send message to my WhatsApp number in the description. So now I want to prove it cannot be correct for x2 to n minus 2. How? I know n choose x is n factorial, x factorial, n minus x factorial. And then I can say, okay, it's n minus 1, n minus 2, 2 what? N minus x plus 1, if we cancel with n minus x factorial over x factorial, less than or equal n. Now we can say n times n minus 1, n minus 2, 2, n minus x plus 1, less than or equal n times x minus 1 times 2. Here, how many numbers are there? This last one minus first one plus 1, x numbers. Here, how many numbers are there? We can ignore 1, so x minus 1 plus this x numbers. This less than or equal this. We can cancel n from both sides. And we know that n minus 1, because we have x minus 1 numbers, consecutive numbers, x minus 1 numbers, because it is less than or equal this, so greatest one should be less than or equal this. So n minus 1 should be less than or equal x. And we can conclude x is at least 2, okay? Because you can consider x, because we said here, we should consider only x at least 2 and this. So this one, because the beginning number is 2, x is greater than or equal to, so n minus 1 is less than or equal x minus x. So, but that's a contradiction because we said that x is less than or equal n minus 2. Maybe you say, okay, for x1 0, what about this case, for example? This one should be correct. When x is 1 or 0, it's not x to 2 because we considered x to 2 means x is at least 2. Okay, so we reached contradiction for x between 2 and n minus 2. And it was the proof for this problem. Again, we solved this problem by considering a small example because it was related to graph permutation graph. Let me tell you the SUMIC problem that can be solved with similar idea. Okay, Stanford University Mathematics Camp, SUMIC 2022. Summer camp for Stanford, problem 4. Again, you can solve it with permutation graph. You can do it as homework 1. If you want to solve more similar problems and want to learn important background ideas, as I said before, feel free to send message to my WhatsApp number in the description. JMO 2024 problem 5. It says find all functions f from R to R, real numbers to real numbers, that satisfy f of x squared minus y plus 2y f of x is equal to f of x plus f of y for all x and y in real numbers. Okay. For solving functional equations, one idea is you should consider again small examples, for example, 0, 1, -1. Idea 2, you should consider spatial cases, for example, x equals y and something like that. And there are lots of things you should consider. Is it 1 to 1? And if you have complicated term, try to get rid of that. I will tell you how. Now here, let's first consider spatial cases. For example, the first special case, because we have from real numbers. If you had, for example, from positive real numbers to positive real numbers, we couldn't say x, y, 0. Here, because they are from real numbers to real numbers, the function, we can consider x is equal to y is equal to 0. Then left hand side would be what? F of 0. This one's 0 because y is 0. Is equal to f of 0 plus f of 0. We can cancel f of 0 from both sides, and so f of 0 is 0. Here we can consider, we can say that, suppose that f of 0 is a constant, we know a constant c, then we can say f of c is 0, okay? So, let's put a box around the things that maybe can be useful. It's first one. Now, let's consider only x is equal to 0. Then it would be what? F of -y plus 2y f of 0 is equal to f of 0, which we said it is equal to 0 plus f of y. So we can cancel this. F of 0 is c. Why we can cancel this? Because of this. So we can say f of -y plus 2yc is equal to f of y. Okay. Let's put a box around this second important result. Now, let's consider y equals 0. Then it would be f of x squared here. This is 0 is equal to f of x plus what? Plus f of y, which is plus f of 0. F of 0 is c. So, let's again put a box around this equation, and we can call it third result. Look, always when you want to solve a problem like this, you don't know which of the results are useful, which of them not. So we write all of them. We label them, for example, 10 results. And maybe at the end you will understand that, okay, 6 of them were useful. In the beginning, how can we understand which of them are useful? We cannot. So write down all, or put a box around all results that you think maybe can be useful. Now, next step, we can consider what? We can consider x is equal to y. Then it would be what? F of x squared minus x plus 2x f of x is equal to f of x plus f of x. Okay. Let's put a box around this one. Fourth result. Okay, next. Then we have an equation like this. And one term is not good. F of x. Okay, sometimes you have a complicated term like this. And we want to get rid of that. Okay, so idea 3. Get rid of complicated term. Complicated term. Okay, how I don't like this. So I consider y1 and y2. 2y1 and f of x squared minus, now with y2 plus 2y2 f of x. Here at the end we can understand that it's not useful, but in the beginning we don't know which of them is useful. So I tried also this one, and if we subtract, these two things will be cancelled. This part will be what left hand side? will be f of x squared minus y1 minus f of x squared minus y2 plus 2f of x times y1 minus y2 is equal to f of y1 minus f of y2, okay? Now, let's put the box around this part. We can write it as fifth result. Okay, now in next step, I want to consider this one. I want to see, for example, how can we get rid of this part. So, if this one is 0, then f of 0 we know is 6. If I consider y is equal to x squared, then it will be f of 0. We call this one c. Now, first box here, f of 0 c, plus 2x squared f of x is equal to f of x plus f of x squared, okay? And, okay, if you write it in terms of c, we can say, can we simplify? Okay, so let's put a box around this part. Let's call it a sixth result, okay? Okay, now let's consider all things that we reach, which of them are similar. This one and this one can be useful because both of them have f of x squared and f of x. So let me consider third result and this one. Okay. If we combine these two things together, we can, instead of f of x, I can write f of x squared minus 6. So let's write it. From 3 and 6, we can say, okay, c plus 2x squared f of x, c plus 2x squared f of x is equal to f of x from third one is equal to f of x squared minus c. So f of x squared minus c plus f of x squared. Okay. If we take negative c to left hand side and simplify, it's 2c plus 2x squared f of x is equal to 2f of x squared, okay? And now we can divide both sides by 2. So c, we can switch left hand side and right hand side. F of x squared is equal to x squared f of x plus c. Okay, we can call it result number 7, okay? And that can be useful. Why? Because we proved that f of c is 0, okay? So if I replace x with 0 in this one, then f of 0 is equal to c. So we've not reached any important result. Okay, so we've reached an obvious result. Now, let's see things that we have. Let's consider again third result. From here, if we consider f of negative x, okay, f of negative x squared is x squared. We change x to negative x is equal to f of negative x plus c. This is equal to this one. This is equal to this one. So we can conclude what? We can conclude f of x is equal to f of negative x. One term is left for each of them. So that term should be equal. And in next step, we can say what? Here again. If we consider this one, and if we change again x to negative x, then we have c plus 2x squared f of negative x is equal to f of negative x plus f of x squared. We know this and this are equal because of this part. So let me draw a box around this. It will be result number 8. So because they are equal, and this part also equals, c equals, so we can conclude 2x squared f of x is equal to 2x squared f of negative x. So consider that x is not 0, okay? If x is not 0, then we can conclude f of x is equal to f of negative x. And because when x is 0, we know f of 0 is equal to f of y. We should consider x is not 0 because we want to cancel x squared. It shouldn't be 0. Then we can conclude this. If x is 0, then f of 0 is equal to f of negative 0 because negative 0 is 0. So we can remove this and it's correct for all x's. So let me draw a box around this. It is 9. And f of x is equal to negative x. If we use 9 here, this one is equal to this one. So we can say 2y c0, so c is 0. Okay, so let me combine this from 2 and 9. 2 is this one, 9 is this one. Okay, so from these two results, we can conclude what? We can say, okay, we can cancel these two things. So 2y c0. And then we can select one y that is not 0. You can say, for example, y is 1. Okay, when you want to use this. So 2c0, so c0. So let's put a box around this one, and it will be our 10th result. Okay, because c0, we can write this one, and we can say what? Because c0, we can write f of x squared is equal to x squared f of x. Also, we can say what? We had something about f of x. Because c is 0, you can cancel this, and f of x is also f of x squared. From 3 also, you can say f of x. Also by using 3, we can say f of x is equal to f of x squared is equal to x squared f of x. Okay, so let's put the box around this one, and it will be result number 11. Okay, because now we have f of x that is equal to two things. Let's calculate f of x two different ways. So we can say what? If we use this part, we can say f of x, if we use this part, is f of x squared. So we can write f of x squared. And then we know f of something, we want to use first one, last one. F of something is that squared. So here, x squared f of x squared. So it would be x to the 4 times f of x squared. Then we should use second one and third one. F of x squared is x squared. So x squared times x squared f of x, which would be x to the 6 times f of x. Okay, so let's review what we did here. Suppose it is 1, 2, 3. This part I said, okay, f of x is f of x squared. So I used 1 and 2. And then f of x squared is equal to this. We used 1 and 3. And then f of x squared is equal to x squared f of x. So we used 2 and 3. Now let's calculate it with another way. We can say f of x. Here you can say, okay, it is f of something. We want to use 1 and 3, okay? So f of something is that thing, which is f of x squared, and f of x. And then for f of x, we want to use this 1 and 3. So it will be f squared x plus, or let's write like this, f of x squared, f of x for 1 and 3. It's what? X squared f of x. So it will be x squared times f of x cubed. So we can conclude these two terms are equal. So x to the 6 f of x is equal to x squared times f of x cubed. Now we can do what? We can cancel x squared from both sides. Consider x is not 0, okay? Because when x is 0, we know obviously it's correct. And at the end, we will consider. Let's divide both sides by x squared. So it would be x to the 4. And let's do something. Suppose x is not 0, f of x also is not 0, okay? At the end, we say, okay, one case is that f of x is 0. So if we simplify, we can divide by x squared f of x. So it will be x to the 4 is equal to f of x squared. So from here, we can conclude f of x is equal to plus minus x squared, okay? From real numbers to real numbers. So we can conclude f of x can be 0, because here we consider it's not 0, or plus minus x squared. Now we want to see, is it possible that for some x's f of x equal to 0, for some x's f of x equals plus x squared, or something like this? Because we have three different values. X squared, for 0, all of them are equal. Let's consider the cases that are not 0. I want to see, is it possible to have both 0 or x squared, or both 0 and negative x squared, or both negative x squared and x squared? I want to reject all of them. Then at the end, we can conclude all f of x should be 0, all f of x should be x squared or negative x squared. So let's check these cases. Suppose, okay, let's copy our main equation. Okay, this one. And here, suppose that f of, for example, x1 is 0, and f of x2 is, or let's write y1, is what is y1 squared. We want to check this case, okay? And we can consider that x1 and y1 are not 0. Why? Because if they are 0, then for f of 0, all of them satisfies. So 0 is not important, because 0 squared plus minus 0 squared would be 0. For non-zero values, we want to see, is it possible that one of them equal to 0, one of them y squared, or not? So if we replace f of x1 squared minus y1 plus, because f of x1 is 0, we can cancel this. F of x1 is 0, we know f of 0 also is 0. We proved, where we proved here, we proved C0 in which part? Result number 10. So f of 0, 0, f of y is what? F of y1, okay? Which is y1 squared. Now we can say what from here? You can say, okay, this one is 0. It's not possible. We have three cases for this, because we said each function can be, let me put a box around this. It will be result number 12. From result number 12, we know that this one is 0, or x1 squared minus y1 whole squared, or negative x1 squared minus y1 squared. Let's check all of them. 0 is not possible, because then 0 is y1 squared and y1 would be 0. We said in the beginning y1 is not 0. If we check next one, x1 squared minus y1 squared is equal to y1 squared, then we can raise the left hand side to the power of 2x1 to the 4 plus y minus 2x1 squared y1 plus y1 squared is equal to y1 squared. We can cancel y1 squared from both sides. We can divide both sides by x1 squared. So x1 squared minus 2y1 is 0. And okay, we can conclude what? We can conclude x1 squared is equal to 2y1. Okay, it is case 1 that we are considering. Okay, case 1. Now, in next step, we can say what? We can consider x1 and negative y1, because we know f of negative y1 is equal to f of y1. We proved this in result number 9. Now, if we consider this part, f of x1 squared plus y1, again, this part is 0, because f of x1 is 0, this one 0, f of y1, f of negative y1, which is f of y1, y1 squared. Again, you can say this part can be 0 or x1. Sorry. I didn't consider last case, this one. We can reach contradiction for this one. Why? Because from here, negative x1 squared minus y1 whole squared is equal to y1 squared. You can take it to right hand side. So x1 squared minus y1 squared plus y1 squared is equal to 0. And because they are real numbers, they are at least 0, so we can conclude both of them should be 0, y1 0, that's a contradiction. So the only thing that we can consider is what? x1 squared is 2y1. Now here again for 0 we can reach contradiction for x1 squared plus y1 whole squared and negative x1 squared plus y1 whole squared. Again for this one you can reach contradiction like this. You can take this to right hand side and you can see it would be 0. For this one, if we expand x1 to the 4 plus 2x1 squared y1 is equal to y1 squared. You can cancel also y1 squared, it would be 0. So if you divide both sides by x1 squared, it's not 0, so you can write x1 squared plus 2y1 is 0. Now if we combine this one and this one, x1 squared is 2y1, so if we replace 2y1 plus 2y1 is 0, so 4y1 is 0, so y1 is 0. Again, that's a contradiction. Okay, so case 1 is not possible. We've reached contradiction for case 1. Now let's consider case 2. 0, negative x2. Again, by similar approach, we can reach contradiction. x1 f of, okay, let me write case 2. F of x1 is 0. F of y1 is negative y1 squared. X1 and y1 are not 0, okay? So we write f of x squared, x1 squared minus y1 squared minus y1. This one 0, this one 0, because f of x1 is 0 is equal to f of y1. Like previous case, you can say, okay, f of x1 squared plus y1 also is equal to f of negative y1. Both of them are negative y1 squared. They are equal. We proved this before. Now, we should check again different cases. We know it cannot be 0. And like previous case, it cannot be this one squared, because then you can take these to left hand side, sum of 2 squared 0. Each of them should be 0. So the only possible case here we have is negative x1 squared minus y1 squared is equal to negative y1 squared. And for this one, x1 squared plus y1 whole squared, negative of that is equal to negative y1 squared. Okay. Now from this part, we can cancel negative 1 from both sides. Here we can cancel y1 squared from both sides, x1 to the 4 plus 2x1 squared y1 is 0. Minus. And from here, x1 to the 4 minus plus 2x1 squared y1 0. Then if we subtract this minus this, or we can add 2x1 to the 4 is 0, so because x1 is a real number, x1 is 0, that's a contradiction. Okay, so we reach contradiction for the second case. Now, third case. X squared negative x squared. So, third case. So, let's write f of x1 is x1 squared, f of x2 is f of y1, let's write y1, is negative y1 squared, okay? And our main equation is what? Is this one. So, let's replace again. We can say what? F of x1 squared minus y1 plus 2y1. F of x1 is x1 squared. F of x is what? X1 squared. F of x1 squared is, we should consider. Because we proved f of x is what? We proved f of x is x squared f of x, okay? So, because this one is x squared f of x, and we know f of x1 is x1 squared, so x1 to the 4 minus y1 squared, okay? And also we can say what? We can say f of x1 squared plus y1 minus 2y1. Here we consider x1 and negative y1. x1 squared is equal to, again, x1 to the 4. F of y1 and f of negative y1 are equal, so both of them will be negative y1 squared. Okay, now we can conclude what? F of x1 squared minus y1 is equal to x1 to the 4 minus y1 squared minus 2y1 x1 squared, okay? And f of x1 squared plus y1 is equal to x1 to the 4 minus y1 squared plus 2y1 x1 squared, okay? So let's check each of them. For example, this. For this one, we know we have three cases. It can be 0, so, or it can be this one squared, so x1 to the 4 minus y1 squared minus 2y1 x1 squared is equal to x1 squared minus y1 whole squared, or negative of that. So let's check negative of that. So here, if we simplify, x1 to the 4 will be cancelled from both sides. So negative y1 squared minus 2y1 x1 squared is equal to y1 squared minus 2y1 x1 squared. So you can cancel these two sides, so y1 is 0, and that's a contradiction, okay? From here, what can we conclude? x1 to the 4, x1 to the 4. Here, it would be negative x1 to the 4 minus y1 squared plus 2y1 x1 squared, okay? And then we can cancel negative y1 squared, and so it would be, if we take it this to left hand side and this one to left hand side, so it would be 2x1 to the 4 minus 4y1 x1 squared is equal to 0. We can divide both sides by 2, so x1 to the 4 minus 2y1 x1 squared is equal to 0. Because x1 is not 0, we can divide both sides by x1 squared, so x1 squared minus 2y1 is equal to 0. Okay, so we have two cases here. One case is this one. One case is this one. Okay, now let's consider second equation. Again, this one can be 0, one case, or this one can be x1 to the 4 minus y1 squared plus 2y1 x1 squared can be this whole squared, x1 squared plus y1 squared. Or we can say what? We can say this one is equal to negative of that, okay? So here we have x1 to the 4 plus 2y1 x1 squared plus y1 squared. We can cancel x1 to the 4. We can take these to right hand side, these to right hand side, so 0 is equal to, and we can divide both sides by 2, y1 squared plus, oh, we can cancel also something. We can cancel this and this. Okay, so y1, 2y1 squared is equal to 0. So y1 is equal to 0. That's a contradiction. For this one, we can say negative x1 to the 4 minus y1 squared minus 2x1 squared y1. Now we can cancel negative y1 squared from both sides. We can divide x squared. Let's take all things to left hand side. We can say 2x1 to the 4 plus 4y1 x1 squared is equal to 0. We can divide both sides by 2x1 squared. So it will be x1 squared plus 2y1 is equal to 0. Okay? So now again we have two results. This one or this one. Now let's consider the thing. So we should consider four cases. From first equation, we can reach this or this one. From second equation, we can reach this one or this one. Okay. Now we should check. Let's consider these two things first. If we consider these two things, then x1 squared is 2y1 from here. X1 squared is negative 2y1. So 4y1 0, so y1 is 0. Okay, so we've rejected this case. Let's use different colors for proving each of them. Now let's consider this one. From here, x1 squared is 2y1, and if we replace here, it's 4y1 squared minus y1 squared plus 2y1 times 2y1. 4y, it is equal to 0. 4y1 squared, 4y1 squared, 8y1 squared minus y1 squared, 7y1 squared is equal to 0. So y1 is 0. Okay, again, that's a contradiction. Now let's consider this one. Again, by similar approach, you can say, okay, x1 squared from here is negative 2y1, and if you replace it here, it's 4y1 squared and minus y1 squared minus 2y1 minus 2y1 is equal to 0. So again, 4 plus 4, 8 minus 1, 7, y1 squared is equal to 0. So y1 is equal to 0. Okay, that's a contradiction. Now let's check last one, this case. So if we subtract this or this minus this one, x1 to the 4 and negative y1 squared would be cancelled. So 4y1 x1 squared is 0, and that's a contradiction because we said x1 and y1 are not 0. So we reach contradiction, we can have only one of them. So first answer is f of x is equal to 0 for all x's. Say next one, f of x squared. And last one, f of x is equal to negative x squared. Let's check our answers. So main equation is this. Always check in main equation because maybe you have careless mistake. You should check it like this. So for 0, case 1. 0, 0, 0, 0 plus 0, 0. So it's correct. Second one, f of x squared. This one would be x squared minus y squared plus 2y x squared. X squared would be x to the 4 plus y squared. Is it correct one? If you raise this side to the power of 2, it's x squared minus 2y x squared plus y squared plus 2y x squared. Y, it is equal to x to the 4 plus y squared. 2y x squared, negative 2y x squared would be cancelled, so x to the 4 plus y squared, x to the 4 plus y squared equal. So it is our second answer. Let's check third one. For third one, we say what? It is equal to negative x squared minus y whole squared plus 2y negative x squared, and this one, it's f of negative x squared plus minus y squared. And this part would be what? Negative this one squared, negative x squared squared. We want to see are they equal or not? Minus y squared. This one would be what? Minus x to the 4 minus y squared plus 2yx squared minus 2yx squared. So we can cancel these two terms. Here it would be what? Negative x to the 4 minus y squared. They are equal. So we proved third one also is an answer. Let me tell you a homework to solve similar to this one. Okay, try this AIME problem as homework 1. If let's review what are the ideas we used. Idea 1, 2, 3, get rid of complicated term. And then, I can say one more important idea, idea 4. Try to, for example, when you use 3, we try to find something inside itself. We calculate something with two different ways. We can call it also double counting is for combinatorics, but with two different approach you can find something. When you can find something inside itself. Idea 4 and okay, you should check at the end. You should check these things. Okay, 4 ideas. And then you can try this AIME problem. This is a common problem in JMO 2024 and AIME 2024. It says point D is selected inside acute triangle ABC. So that angle DAC is equal to angle ACB. So it says DAC is equal to ACB, or we can call it C. And BDC, this angle is 90 plus BAC, or 90 plus A. Okay, so this angle is 90 plus A. Then it says point E is chosen on ray BD, so that AE is equal something like this. BD, so that AE is equal to EC. Okay, so we can conclude that E lies on perpendicular bisector of AC. So if we draw perpendicular bisector of AC, because AE is equal to EC, and BD, the intersection is E. So our E is this point, and intersection of this perpendicular bisector and this one. Then it says let M be the midpoint of BC. Okay, midpoint of BC. So let's consider BC to 109. Some point like this one. AE and EM are not, we can say AEM are not collinear necessarily. So we can consider this one, midpoint. And then it says what? Show that AB is tangent to the circumcircle of triangle BM. Okay. When a line is tangent to the circumcircle of a triangle, we can say what? This one, this one. We should prove we know. Here it is alpha, here it is alpha, here it is beta, it is beta. We should prove one of them. So we should prove this one is angle beta, or we can extend this, extend AB, like the thing I said here, and prove that this angle is equal to this angle. This angle is what? Is 180 minus B. So proving this one is 180 minus B is better. It's better to not use new angles. So we should prove this angle is 180 minus B. Let me show it with alpha. I should prove y alpha is equal to 180 minus B. Now, there are some things that we should, some lines, some circles we should draw. Why? Here, as you can see, E lies on perpendicular bisector of this. So we can say it passes through circumcenter of ABC. So because of this, we draw circumcircle. Can be useful because we see, okay, En passes through that. We draw, maybe useful, maybe not. Like functional equation, if we think something can be useful, we should apply that. Okay, at the end, for example, we apply 10 things, 6 of them are useful. Okay, so if we draw this, let's see what happens. We should prove alpha is equal to 180 minus B. If we prove this, the problem will be solved. Now, here we draw this one, and another thing that can be good. By midpoint theorem, we know that if we have this, and I am also this idea useful. When we have this, it is parallel to this one. And we want to prove this angle is 180 minus B. And we have one midpoint. So if we extend this such that E is the midpoint of this line, we can say it is parallel to this one, EM. So let's extend BD. So it is what? It is 106. 212. And let's draw this one. So BDE. We have E, so let's call it F. Okay, now we know this angle is alpha, so we should prove this alpha is 180 minus B. Okay, now if we extend this line, because we know that it is angle C, okay, and if we extend this, we can say something about arcs. Extend what? Extend AD to intersect our circle. Because this angle is C, if we draw this one, we can say this angle is also C, okay? And we can also connect this to this, CFG, HI. Let's consider this one as J. So what can we say here? This angle is what? This angle is B. Because of this. This angle is, the whole part is A. It is B. And this angle is what? This angle, because this is 180 minus 8. This and this are 180. So it is BC. So this one has to be 8. Because this quadrilateral, some of the angles Should be 360 in this quadrilateral. Now, let's see what are the other angle chasing that we can use. One thing here that we can pay attention is this is alpha. We want to prove it is 180 minus b. It is b. So we should prove JDFC cyclic. So it is equivalent. When you want to work on a problem that is a bit hard, try to work a bit on assumptions, a bit on the sentence of the problem. It is equivalent that JDFC is cyclic. And I told you 4 rules for proving a quadrilateral is cyclic. Let me paste out 4 rules are what? I told you for first problem of JMO, we use this one for JMO, problem 1. Now here we want to see which of them is useful. Because here we are working on angles, and these two things can be useful. And we use one of them, we want to prove this plus this 180. Which angles are good? Because it is 90 plus A, we can say this angle is what? 90 minus A. So if we connect FJ, it is not, it doesn't, we should check it, but we cannot consider it passes through M. So let's consider something like this. Let me change M a bit more. Okay. And this line. Okay. We should prove J1 if it is 90 minus A, we should use second rule, okay? We should prove why J1 is 90 minus A, okay? It is equivalent that J1 is 90 minus A. So we know this angle was A, right? Because we said if we consider this cyclic quadrilateral, it is B, it is C. This plus this is 180. Because it is B, it is C. B plus A plus C is 180. So because we know this is A, if we want to prove J1 is 90 minus A, so we should prove, let's call this point K. We should prove why K is 90 degree. Okay? K is 90 degree, it is equivalent. If it is 90 degree, this line and this line should be parallel to each other. En is parallel to Fj. Okay? Now we can extend En. And as you can see, we know it is A, it is B, it is C, so this angle is also A. So these two lines are parallel to each other. Also, we said E is midpoint of this. So these two lines are parallel to each other. Also, you can conclude, you can draw MN, and MN is parallel to AB. All parallel lines. Let me write it here. MN is parallel to AD. All of them by midpoints theorem, or Thales's theorem. Then, what can we say here? We want to prove it is parallel to this one. So, we proved it is parallel to this one, and this angle is A, this angle is A. So we can say all things are symmetric with respect to this line, okay? It is what? An isosceles trapezoid. So if we extend En, we can say these two figures are congruent. It is 90 parallel, it is 90. Now we know because it passes through, it is perpendicular bisector of AC, it is also perpendicular bisector of BJ. So this one, 1, 2, 3, 4, they are equal. So let me write it with other colors. This is equal to this one. Now, again by midpoint theorem, we know B is equal to EF. It was the way that we've defined F. So we can say what here? We can say, let's call this point KL. Okay? We can say, because it is equal to this one, BE is equal to EF, and BL is equal to LJ, so this line is parallel to this one by this point, midpoint theorem, or Thales's theorem. So we can say this line is parallel to this one, so we can say k is 90. Okay, it is parallel to this one, k is 90, so j1 is 90 minus a, so jdfc is cyclic, and alpha is 180 minus b. So let's consider the ideas that we worked on. First idea, this cyclic quadrilateral symmetry that we call, so okay, all things are symmetric with respect to perpendicular bisector of AC. Midpoints theorem, obvious thing. By similar triangles you can prove it, and it is a special case. We know if this over this is this over this, it is equivalent that these two lines are parallel to each other. And angle chasing, all these things, okay? So, if you had any question about this problem or wanted to solve more similar problems, as I said before, feel free to send message, my WhatsApp number in the description. Okay, you can try this. There are some ideas in geometry, and for example, one of them is to how to create equal angles to find cyclic quadrilaterals, like this problem. Okay, so try this one as homework 1. This IMO 2019 problem 2. If you wanted to solve more problems or want to learn more ideas, as I said before, feel free to send message, my WhatsApp number in the description.